Right. In the previous video, we looked at the work function and we said that if the frequency of the incident light is equal to the threshold frequency of the metal, then the energy of the photon is just enough for the electron to be emitted from the surface of the metal. So we looked at the minimum amount of energy. Now we're looking at the maximum kinetic energy of the ejected electrons, and we're looking at EK max. So what's going to happen is, when I have a metal and I shine a light onto it, there's one of two things that's going to happen. The first thing that's going to happen is that inside this metal, the electrons will move to the surface of the metal. So what we're looking at then, when we mean the surface of the metal, we're looking at this zone on top here. Right? So that's the first part. Now, in order to move to that surface, they must have just enough energy. Right? Once they have enough energy or they've got a lot of energy, they're going to be ejected. So the second part is that the electrons leave the metal. Now, the only way that they can leave the metal is by moving. And in order to move, they must have some sort of velocity. And if they have velocity, they will have kinetic energy. Right? So what I'm seeing here in this motion of the electrons leaving is I've got kinetic energy. So the goal here is to get enough energy to not just get them to the surface, but to get them to leave the surface. So how that happens is, if we say that if the frequency of the incident radiation, in other words, the light that we use, is greater than the threshold frequency, then the energy of each photon will be greater than the work function of the metal. Alright, so let's understand that a little bit. So, if I had it less than, so far this is what I had. If the frequency of the incident radiation was less than, then I had no electrons. Right? If my frequency was equal to, then I had some electrons, but also I had enough energy. And here I had not enough energy. Now we're saying that if it's greater than, all right, then all of the energy of the incident photon is transferred to the electron. To the electron. So those are my three conditions. I need the frequency of the incident ray to be greater than the threshold frequency, so that the energy of the photon is greater than the work function of the metal, right? And so let's just talk about that energy. Let's say I had a little box here of energy, right? And I had these little bits of energy everywhere. Use two colors. Okay. Right. Two things are going to happen with the energy that's coming through here. Some energy, let's say all the red energy, is going to be, so this is energy, let's just use another color. This is the energy of the incoming photon. That's what's in this little box here. We can say that some of the energy is used to move electrons to the surface of the metal. And we call that the work function. So I showed you in the diagram above. The rest of the energy, let's say the green stuff, is transferred to the electron as kinetic energy. Alright, so that's the second thing that's happening. Now, if the electron has kinetic energy and it has this EK over here, it will be ejected, or we can say it will leave the metal. And that's how we end up with this situation here. Because it gets kinetic energy, it's able to move. And if it moves, it has some sort of velocity. So the electrons that we're dealing with here, I should just add to this. When we talk about the electrons here, we're talking about the electrons in the outermost shell, outermost energy level. From Bohr diagrams, that idea of the metal atom, right? These electrons, are called the valence electrons. And these valence electrons will have maximum kinetic energy. Right. They're going to have the most amount of kinetic energy because, like I said, they're going to end up leaving the metal. Now, when we do calculations for this little section over here, we come up with a formula. If I wanted the energy of a photon, it's going to be equal to the work function plus the maximum kinetic energy. Kinetic energy. Alright, so how we would write that down? I know energy of a photon is E. I know work function is WO. And I know that kinetic energy is EK. And we're going to call it EK max. Like that. So this is your formula. Now, of these formulas, each of these things have their own formulas. For example, I know that for E, for energy of a photon, I still have E is equal to HF, and I have E is equal to hc over lambda. So that's one. I know for work function, the formula for work function is WO is equal to HFO. And I know that for EK, I have the formula, right, of half mv squared max. So each of this main formula here doesn't just stand by itself. It means that we can use any of the sub formulas that they actually belong to in order for us to do calculations depending on what kind of information they give us. So let's say, for example, they're asking for energy of a photon, and they're giving you the work function, and they're giving you, I don't know, maximum EK, and they're giving you some other bit of information. You're allowed to use any of these formulas in place of E. You're allowed to use this formula in place of work function, and you using this formula here for EK. Now, one of the most common formulas that they, or most common things they ask us to find, is they ask us to find the velocity, or the maximum velocity of the electron. So we're going to look at a little example now where we see how we do these types of calculations. It says here that the threshold frequency of cesium is 4.71 times 10 to the power of 14. They want you to calculate the maximum speed of an electron when blue light with a wavelength of 420 nanometers is shone on a cesium surface. So in terms of information, let me just have a look at what I've got. I've got FO at 4.71 times 10 to the power of 14 hertz. I've got lambda at 420 nanometers, which I'm going to change obviously into 420 times 10 to the power negative 9 meters. They want velocity, so they want Vmax, and that's the information that I have here so far. Right, other information that I can take from my formula sheet would be things like H, which is 6.63 times 10 to the power of negative 34 joule seconds. I have C, which is 3 times 10 to the power of 8 meters per second. Right. Now, if they want Vmax, Vmax belongs to EK. Now, EK has mass. Now, we're looking at an electron. So the best thing to do is unit mass of an electron. They give that to you. You'll find it on your formula sheet. And you've got mass of an electron at 9.1 times 10 to the power of negative 31 kilograms. All right, so you've got the mass, and you're looking for Vmax. And this is the other bits of information that we do have. All right, so I need to find a formula that works for me. So the problem here is I don't have work function. Okay, let's just use another color. I don't have this, but I do have that. If I look here, I don't have this, but I do have options. Of these options here, I've got lambda. So now I've got to use all of the information, and I know I've got EK, so that's great. I've got to put together what my equation is going to look like. So the first thing I do is I write down the base equation, which is E is equal to the work function plus EK max. Right. Even though I'm not using that, that's my base formula. That is what I'm getting marks for. Now for E, I'm going to have to use what I have, which is HC over lambda is equal to work function I don't have, but I do have H and I do have the threshold frequency. So I'm going to go HFO plus EK max is half mv squared max. All right, so that is the formula that I'm working with now for this equation. So all I've got to do now is substitute my information. I know H is 6.63 times 10 to the power of negative 34. And that is going to be multiplied by 3 times 10 to the power of 8. And all of that is going to be all over 420 times 10 to the power of negative 9. So that's the first thing that I have there. 9 looks a bit dodgy. Equals to H again, which is 6.63 times 10 to the power of negative 34. All multiplied by my work function, which is 4.71 times 10 to the power of 14, plus, move it across here, half. My mass of my electron is 9.1 times 10 to the power of negative 31, all multiplied by V squared max. Alright, now I've got to do some sort of solving. So I'm going to start on my left-hand side, pop this into your calculator, and I'm going to get 4.736 times 10 to the power of negative 19. That's the first part. The second part I'm going to do, so how I'm doing this is, the first thing I did was this. That's number 1. The second thing I popped into my calculator, that's number 2. And here I got, let's change my pen, 3.123 times 10 to the power of negative 19. And then the last step that I did was this little bit, and I halved that, which is number 3, part 3. And I got plus 4.555 times 10 to the power of negative 31 V squared max. Alright, if I look at these values, what I can do is I'm going to move this over to this side and put a minus sign, and I'm going to get 1.613 times 10 to the power of negative 19 is equal to 4.555 times 10 to the power of negative 31 V squared max. Alright, next thing I need to do is get V squared max by itself. So divide both sides by 4.555 times 10 to the power of negative 31. And I got V squared max is equal to 3.541 times 10 to the power of 11. Square root both sides. Let's keep this together so we can keep an eye on our calculation. And V max is equal to 5.95 times 10 to the power of 5 meters per second. And that is my final answer. So it does take a little bit of work. It does take a little bit of analyzing and thinking. But the best thing that you need to do, or the best way to get through this type of a question, is to get down all of that information. Look at all the information you have, and then you need to make a judgment as to how you're going to divide this major equation into something that is workable for you, so that it's easier for you to do a calculation like this. But this is not an advanced question. An advanced question would require us pulling information of graphs. The question will come to us in a more complicated way. But the basis of it is you need to know how to be able to do these types of calculations by manipulating this major equation into something workable. The next little thing we're going to look at is the intensity or brightness of electromagnetic radiation. So when we talk about brightness, we're looking at how far light can reach. For example, if I had a car and that was the headlights, then if I had a normal brightness, then that's what I'd be looking at. But if I had to put on the brights, then I would be looking at something like this, which is a bit bigger. And so that's what we talk about when we talk about the intensity of light. So what we need to understand is, how does the intensity of the light affect the number of photons that arrive onto the metal surface? So if we increase the intensity of the light that is shown onto the metal surface, it will increase the number of photons arriving. So that's the first thing. It's going to increase the number of photons per second. If we have more photons per second, then more electrons will be ejected per second. So one photon is absorbed by one electron. So every photon is going to give me another electron. So if I have more photons, right, then I'm definitely going to get more electrons. But if I change the intensity, it does not change the frequency or the wavelength. So what that means is, I can have a radio wave, right? And that radio wave has a certain frequency. So let's say, for example, it has a frequency of 300 gigahertz, and it has a wavelength of, let's say, 100 kilometers. That frequency and that wavelength, no matter how intense I make that light wave, it's not going to change that radio waves function at 300 gigahertz and can only reach up to 100 kilometers. So what we're saying is, our frequency is related to how much of energy is coming through. So if we change the intensity, it's not going to affect the frequency, so the hertz stays the same, and it's not going to affect the wavelength. It's still going to reach the same amount. So if I use a brighter light, it still doesn't affect it the way I want it. It doesn't affect it in a way that we would think it would affect it. So all we do with increasing the intensity is you increasing the number of photons, which means more electrons ejected per second. But changing the intensity doesn't change the frequency, because if I change the frequency or I change the wavelength, I'm affecting the type of light, because it is set, it's constant. Radio waves have a certain frequency, infrared, gamma rays, microwaves, visible light, red light, blue light, frequency stays the same, wavelength stays the same. So a change in intensity will also not change the energy of the incoming photons. It's just going to be more photons, but not an energy increase, because that comes from your frequency. So we're going to have a look at a few questions now and see how would we answer these questions in a test or an exam. These notes here, or these points, are in your books. Question number 1. It says, what will happen if we shine a very bright red light of the same wavelength onto a sodium metal? So let's say it has a wavelength of 410 nanometers. That's what we're looking at. Alright, so first of all, we've got very bright, but we've got red light. The first thing you need to notice about red light, please make sure as well as these questions and how we're going to answer them. First thing here, we've got high intensity, but we've got a very low frequency. Now, because we have a very low frequency, we can say that no electrons are ejected. And the reason for this is that red light, right, versus sodium, the frequency of the red light is less than the threshold frequency of your metal, of the light. And if that's the case, then the incident photons is less than the work function of the sodium metal. So you've got two things going. So therefore, an increase in intensity will not change the energy of the photons, right? So suppose we change it, right, and we change the wavelength. So let's just move this out of the way. Right, let's say for example, I change the scenario and I've got a dim blue light, right? And this dim blue light has a lambda value of 480 nanometers. If I shine this onto sodium metal, then the electrons are ejected. The reason for that is blue light has a higher frequency. And if I have a higher frequency, I have more energy. And more energy means more electrons have the energy to overcome this sort of situation. So you've got to look at the words that they're using, and we're going to do a few scenarios like this and see where we get to. And let's have a look at the next thing. Okay. The next one says, what will happen when we shine a very bright light, a bright blue light of the same wavelength onto sodium? Right. If I have more photons arriving per second, right, then I'm going to get more electrons ejected per second. And it's not because it's very bright. Remember, we're still using 410 nanometers. It's not that we're using a very bright light. It's because we're using a blue light, and I just said it has high frequency. So it has nothing to do with whether it's bright or it's not bright or whatever the case is. Now let's have a look at the next little question. Right, the next one says, how will the maximum kinetic energy of the ejected electron change when we shine a very blue light onto a sodium surface? Right, we're looking at maximum kinetic energy, very bright blue light onto a sodium surface. Right. First of all, here, my EK max if I manipulate my formula, is equal to the energy of a photon minus the work function. Right? So what's happening now is you've got this very bright blue light on the sodium surface, and we already know that if I have a blue light, I'm going to have a lot of energy. So therefore, there will be no change in the maximum kinetic energy. Because, like I said, it's not about the brightness. It's about the type of light of ejected electrons. Right? Because the reason for this, there is no change in energy of incident photons. Remember, blue light, there's no change. So what's actually happening here is when the intensity of the light is changed, there's no change in energy and there's no change in the work function. So if I have an increase in intensity in this situation, will result in no change in energy, as in your energy of your photon, and there's going to be no change in the work function. No change of the metal. So that is why if I have a bright blue light on a sodium surface, it doesn't matter whether it's bright or dull or dim. I'm still going to get no change. Right, then the last question here. How will the maximum kinetic energy of the ejected electrons change when we shine an ultraviolet light onto a sodium surface? Right. If I look at my electromagnetic spectrum, and I'm looking at my electromagnetic spectrum, and where my electromagnetic spectrum actually falls, I'm just going to highlight this for you, is here. Right? So two things we know here about the electromagnetic spectrum is that over here we are increasing frequency as we move this way across. And if we increasing frequency, if we increasing the frequency, it means we have more energy available. So if I had to make a statement here, I can say the frequency of the light is higher, and therefore the energy of the incident photons is higher. Right. Now, if I know that on top of everything else, the work function of a metal is constant. Right? If it has a work function, it has a function. So what's going to happen is, because you've got ultraviolet rays and they are much higher, there is going to be a transfer of energy. And that transfer of energy is EK, or kinetic energy. So they want to know, how will the maximum kinetic energy change if the electrons have an ultraviolet light on sodium, you can say that at the end, the maximum kinetic energy of the ejected electrons will increase. So this is how they're going to ask you these types of questions. You need to make sure that you understand relationships, and you understand that if I change this one thing, it's going to affect the system like this. If I change another thing, it's going to affect the system like this. And it all comes down to theory. If you don't know your theory, you're going to struggle to answer these types of questions. And let's go to the sixth subtopic. Topic 6 or subtopic 6 is about a photosensitive vacuum tube, or something we call a photocell. So how do we see the photoelectric effect? We use a photosensitive vacuum tube or phototube, and we use that experimentally. Now for exams and tests and so on, you will need to be able to draw and label this. So I would suggest that you do draw this into your book nice and neatly, proper label lines, so that in an exam situation you can understand what's happening here. Right, the first thing that's going to happen is that I'm just going to zoom into this a little bit, so that becomes the main situation. So this little photo tube over here is just a magnified version of what's happening inside in a more complex way. You can get that little sketch down so that you have an idea of what's actually going on the inside and how it all connects together. So what you've got is we've got light rays coming in, we've got cathodes, anodes, and we are looking at current. Now if I'm looking at this diagram, what you would do is you use highlighters and color pens and so on. And the first thing that's happening here is we've got here an incident light. Now your incident light can be red light, blue light, whatever the case is, any kind of light that comes through. Now this incident light is going to shine onto, it's going to shine here onto the cathode. Right, now this cathode, right, is a emissive material. Your cathode, right, is made up of, let's make a note here. The first thing we know about the cathode it has a negative terminal, and the electrons, let's make a note here, it's made of a metal that will release its electrons, right? So the incident light shines onto the cathode, and when it shines onto the cathode, the electrons, your electrons, let's give them a color, the electrons are emitted. So your electrons leave the cathode. Now electrons, we know, have a negative charge. Electrons are negatively charged, and because they're negatively charged little things, they're going to be attracted to the anode. All right, so they're going to come through and they're going to reach the anode over here. Let's have a look here. and here we've got our anode, and we can see that the anode is a positive terminal. So the motion that we have here, or the idea that we're working with, is that the electron's motion is always going to be cathode to anode. The electrons move from cathode to anode. So that's the motion there. Now, what we're using in this one, we can use a galvanometer, or we can use what we have now as a micro ammeter. And the ammeter is there so that it can detect a current, or it can give us a value for current. Essentially what happens now is these electrons are now going to travel through this conducting wire and it's going to go all the way around. And we know that when electrons move, they create a current. And that's what you have now. So you need to be able to explain what's going on in this diagram. You need to be able to label the diagram and talk about what's happening. So the first thing is we're going to get is step 1 here. I'll label it for you. Step 1, you have your incident light and it shines onto the cathode. That's at point 2. The electrons are then ejected from the cathode, which is step 3 here, and they get attracted to the anode there. They then go through here, through the circuit, or through the conducting wire, through the ammeter, and then we get a current. So you need to be able to explain how this photocell works. What's the workings of a photocell? And we're going to have a look at a couple of questions related to this photocell, and let's just have a look at how you're going to answer these types of questions. Alright, it says suppose we have a blue light of low intensity on the cathode and the micro ammeter registers a current. Right, what will happen to the reading on the ammeter if we increase the intensity of blue light? Right, we need to answer that kind of a question. So the first thing you need to understand is that with the photoelectric effect, for every photon, it only affects one electron. So that's the first thing that you have to understand. Now, if we increase the intensity, we know that an increase in intensity means more photons are arriving on the cathode. Please understand that when you answer these types of questions, you must answer fully. Right. Oops. Per second. Right. If I have more photons per second, that will result in more electrons will be ejected per second. And if I have more electrons coming through, then that means that the ammeter reading increases. So I have a bigger current, or I can say I have more current. Right? So that one's pretty basic. The next one's a little bit more iffy. All right, the next question says, what will happen to the reading on the ammeter if there's an increase in the frequency of the incident light? Now, increase in frequency means more often, right? Your brain's telling you more often. What's going to actually happen is the ammeter reading remains constant, right? Now your brain's gonna say to you, why would it be constant if we increase in the frequency? It means there's more electrons coming in more often. So how I would see this as a problem for you, and why this question is a little bit more difficult, is if the frequency of the incident wave increased, then the kinetic energy is going to increase. So let's look at it like this. Let's say if I have frequency increases, right? Then the kinetic energy, the EK of photoelectrons also will increase, right? So why doesn't the photoelectric current, so that's what we call it. On the ammeter, it reads photoelectric current. So why doesn't the photoelectric current increase? So if I say that the EK of the photoelectron increases, that means the velocity increases. And if the velocity increases, then the number of electrons passing an area in 1 second should increase, right? And therefore, I'm going to have an increase in current. So your brain is going to tell you that if I increase the frequency, this will be my thought process. Frequency increases, which means the EK increases, which means velocity increases, which means I'm getting more electrons passing that certain point, which means the current should increase. But what's actually happening is, in the context of the photoelectric effect, right? This thinking, let me just make a note for you here. This thinking is incorrect, right? In the context of the photoelectric effect, the key thing to remember, like I said before, one photon gives me one electron that will be ejected, right? So current is the measure of how much charge flows per unit time. All right, I know that about current. Now, if current is a measure of how much charge flows per unit time, which is proportional in this case to the number of electrons per unit time, right? So it is proportional to the number of electrons ejected per unit time, and therefore the number of photons per unit time. The energy, this whole situation is not affected by energy at all, because when the photon comes in from the blue light, it's going to affect only one electron. And that electron is going to leave the metal. So I want you to think about it like this, right? Let's say I had a circuit. Let's say I have two circuits, right? Here's my circuit. And let's say I have two circuits. Right, I have two identical circuits here. Let's say I said increase intensity. Right. So now initially I had electrons doing something like this. But now I said increase the intensity. Now by increasing the intensity, it means more photons. And more photons means more electrons. So essentially, what my circuit is now going to look like is something like this. More electrons, which means more current. There's more flow. If I go to the other side and I say increase frequency, right? So here's my electrons. And they fill up the space like this, right? And now I want to increase my frequency, right? What's your intuition may be that the faster moving electrons must imply that there's more flow of charge. Just like a river that starts moving faster if there's a greater flow of water. Now, what's happening here is, unlike a river, let's say I had a river that flowed like this. And in the river, I had little gaps, right? What would happen then is that the water would just go, if the water was flowing, it would just go around, it would go around, it would go around, and it would just keep flowing. It would just go around the gaps and keep going. But that's not the case here. So here we have a situation where if I increase the frequency, I'm increasing the speed. My EK does increase. So an increase in the kinetic energy. So the faster the electrons are moving, the more distance each one will cover before the next one is ejected. So basically what's going to happen is, I've got this electron here, it's going to cover this distance here much faster. And then the next electron comes in. All that's happening now is that if I increase the frequency, the faster the electrons are moving, the more distance each one covers before the next one is ejected. Which means that all it means is that the electrons are more spread out. And if they're more spread out, then you're going to get a constant rate of flow. Right? So it's not so much, if I increase the frequency, my ammeter reading is going to remain constant, because in this sort of situation, energy does not play a role. Yes, an increase in frequency means more energy, and more energy means more EK, and more EK means faster. But that's not what's actually happening. What's actually happening is I just have the same amount of electrons moving much faster, covering more distance. Not that I have more of it, I have the same amount, it's just moving much faster. And that's how you answer that kind of a question. Something that's useful for us to actually know as well is that in terms of the work function, the smaller the work function, the easier it is for the electrons to even be emitted from the metal. Metals with low work functions make good conductors. Things like platinum, gold, silver. This is because the electrons attach less strongly to their surroundings and can move more easily through these materials. This reduces resistance of the material to flow of current, so it conducts really, really well. So another type of question they can ask you is anything related to the work function, and that will be dealing with the metals. So you should know which metals really conduct electricity well or conduct well, and that's, like I said, things like gold and silver, which are truly really the best because they don't provide much resistance and they make electric circuits function much better. Right, the following conclusions can be drawn from the demonstration. The first thing is ejected electrons have a range of kinetic energies from 0 to an EK max. The frequency of the incident radiation is increased. The maximum kinetic energy also increases, but the current doesn't increase. If the frequency of the incident ray is constant, the maximum kinetic energy of photoelectrons is unaffected by the intensity. Essentially then, if the intensity increases, the photoelectric current increases. If the frequency increases, the photoelectric current is unaffected, or we can say remains constant or unchanged. Please make sure you get these 5 points into your books. And then the next thing we're going to look at is we're looking at the significance of the photoelectric effect, and then we're going to look at a little exercise of how we answer questions for the photoelectric effect. The significance of the photoelectric effect. So the photoelectric effect is significant because it made that suggestion that light consists of particles. Now, all of this comes from Einstein. And if you think of Einstein, most people think of E is equal to mc squared. That's C there, speed of light, right? So we're looking at in this here an idea of this section touches on quantum mechanics, forms the basis of quantum mechanics. Photoelectric effect also changed scientists' understanding of light, and they developed the quantum theory of light. The quantum theory of light proposes that light consists of particles, packets of energy called quanta, or we calling them photons, and that light has a dual nature, a wave nature and a particle nature. So that's the significance of it. So while Einstein's understanding of the photoelectric effect was transformative, and it was a discovery in the 1900s, which for us it's not current, I want you to think of things like this: street lights turning on as the sun sets. For example, stopping an elevator. Oops. Door or a motor gate. With your hand by just waving it. When you go to the bathroom, public bathrooms at the mall, you can turn on the tap. All of these things use something we call the electric eye. Now, the electric eye is a name given to a group of devices. These are a group of devices that use the photoelectric effect. Right. Now, all of these devices rely on something we called photoconductive cells or photocells. And we looked at a photocell earlier on, and these cells are activated when light is absorbed by the cathode and it knocks off a free electron, and when this electron is left behind, it moves to the anode and it creates some sort of current. Now, one of these mechanisms where you may not expecting is the next time you go to like the movies, and you must pay close attention to the sound coming out of the speakers. This sound is actually created using the photoelectric effect. The audio tape in the projector booth is a transparent piece of film with varying widths, and the film is fed between a photocell and a bright light by a lamp. As the transparent portion of the film varies in width, the amount of light that strikes the photocell varies as well. As a result, the current in the photoconductive circuit changes with the width of the film strip. That changing current is converted into changing frequency, which creates the soundtrack that you hear. Another place where we see the use of the photoelectric effect is in solar power or solar cells. So basically, if I had a solar cell and I had the sun, and the sun's radiation will hit the solar panel, and when it hits the solar panel, that solar panel will hit off its electrons, and those electrons start to move, and it makes electric current. Other places where you can find, so that's one of the most popular ones. You also can find it in photocopiers. You can find it in fiber optics. You know, when you say I have Wi-Fi, we have fiber. We use it in fiber optics. Also, another place, if you're a photographer, you're into photography, these this idea of the photoelectric effect also comes in, where it what do we call this, exposure meters, sorry, or in digital cameras. And what that does, it controls the amount of light that comes through. And it means, it by doing that, it means you're able to adjust the lenses of the camera, right? So all of these applications, all of these things, even things like at certain malls or at the airport, when you get onto the escalator, it's still, but the minute you get on, the escalator moves. Even conveyor belts, the minute you put something onto the conveyor belt, it starts to move. An electron current flows in these photocells. It can turn on a motor, it can open a door, it can ring a bell in an alarm system. Anything that responds to light, or it can be sensitive to the removal of light. So let's put those points down. Either exposure to light or removal of light. That's the photoelectric effect. Application. So if you have things in your life that if you expose light to it, it works automatically, or you remove light from it and it works automatically, then you've got the photoelectric effect happening right in front of you. Right, the next video that you're going to have a look at deals with problems like exam type questions, past papers, and so on. I'm going to go through quite a few questions with you. There are 7 questions in total. Some are theory based, some are calculation based. Please try and engage with it as much as possible. You can write down the questions if you want. I will make, there is a worksheet that's available in the Google Drive. So you'll see it says photoelectric worked examples. You can print that out and then work with me as we go through it. See if you can answer as much as you can.